This is correspondence between neuroevolution and gradient descent. Colloidal particles in water will undergo Brownian motion and move according to a Langevin dynamics, with a component of their motion determined by the force and by the buffeting of solvent molecules. In this example, though, we're not integrating equations of motion. Instead, we're doing a Metropolis Monte Carlo simulation in which we take the Cartesian coordinates of each particle, add to those small Gaussian random numbers, and accept or reject that proposal according to the criterion shown there. It's been known since the 1990s that these dynamics are equivalent in the limit of small Monte Carlo step size. So without integrating equations of motion explicitly, you can still move particles according to the gradients of their potential energy. So this work shows an analogy between the physical dynamics and neural network training dynamics. So if we replace the particle coordinates and the energy with neural net parameters and the loss, there is an equivalence between the simplest form of neuroevolution and gradient descent. So of course, neural network training methods are usually divided into those that explicitly evaluate gradients and those that don't. Gradient-based methods include backpropagation. Non-gradient-based methods go by a variety of names that include genetic and evolutionary algorithms and Monte Carlo algorithms. And we use results of the 1990s physics literature to demonstrate an equivalence between gradient descent and a form of neuroevolution. So there are lots of things called neuroevolution, just as there are lots of things called Monte Carlo algorithms for molecules. And here we're focusing on perhaps the simplest member of the neuroevolution family. So if we consider training a neural network by sequential simple mutations in a population size 1, the results of the physics literature indicate that this procedure is equivalent to doing noisy gradient descent on the loss function. So if you take your neural network parameters, change each by a small Gaussian random number, and accept or reject that proposal according to the criterion shown there, where beta is a parameter of the method. It's related to the reciprocal temperature in physics, and delta U is the change of loss. Then if mutations are small, then for finite values of this temperature parameter, the effective dynamics of this learning method is gradient descent with an effective learning rate shown there in the presence of Gaussian white noise. For an infinite value of this temperature parameter, the evolution equation is instead clipped gradient descent. But this neuroevolutionary dynamics is equivalent for small mutations to noisy gradient descent on the loss. And if we were to average over a non-interacting population of neuroevolution simulations, we would then have gradient descent without the noise. So here is a simple numerical illustration of that correspondence. We're training a neural network to express a simple function, in this case a sine wave. And we show at the bottom 2 of the weights of the network under gradient descent dynamics, shown in black, and neuroevolutionary dynamics, shown in gray. And the mean of this non-interacting population of neuroevolution simulations is shown in green. So the correspondence expressed by the equations on the previous slide can be seen visually here. So these are 2 weights of a deep neural network containing about 7,000 weights. And at the bottom of the slide, we show the value of all of those weights and biases at the end of the simulation, at the end of training. And as expected from the correspondence equations, the green points, the average of the neuroevolutionary population, essentially lie on top of the black points, showing that the dynamics of these distinct methods results nonetheless in effectively the same trained neural network.